Ho ho ho! Merry Christmas everyone, and welcome to Arithmetica and the Speedy Father Christmas! Ho ho ho!
Hello and welcome to Arithmetica, and a very warm welcome from our special guest.
Ho ho ho!
And welcome to this second video covering our mathematical report concerned with determining an estimate for the average speed in which Father Christmas travels in order to deliver all the presents around the world. We begin this video by applying the necessary algebraic processes to our preliminary results from the first video. The algebra will be very simple and primarily via the use of substitution. As a quick reminder, here are the equations that we have established so far. Let's begin with equation 3. And so by substituting equations 1 and 2 into equation 3 above, we obtain We also note that the formula for determining the surface area S of a sphere of radius r is given by By assumption 8, the Earth is modelled as a sphere, and so from our list of parameters we have by equation 12, and so substituting equation 4 into equation 5 followed by equation 13, we have Now, equation 9 is given by And so, substituting equation 6, we obtain Here are the equations that we have established so far. Finally, by substituting the required results obtained so far, we have hence our model for estimating the average speed in which Father Christmas's sleigh needs to travel in order to allow for the delivery of all the presents around the world is given by Now, you might have noticed that we only have parameters and no variables. This is because of the nature of the objective of the model. However, we could at any stage consider how some of these could vary over time and develop a model accordingly. We also note that we could have simply started out with a list of suitable statistics and just applied the math, rather than go through all of this effort and rigour. However, by proceeding this way, we have better control in its development and can decide which parameters will ultimately be used to express the final formula. Moreover, we also have the added freedom of substituting different parameter values at any time for an alternative evaluation of the average speed. Of course, the main reason is that one of the objectives of the videos in this series is to present it in the context of a mathematical model. For many mathematical models, a report will include an analysis of how sensitive the output of the model is to changes to its input values. This is called sensitivity analysis. The process can aid in the assessment of the model's reliability and for a potential revised model. If overly sensitive to a particular parameter, say, more care is needed when applying the model. A revised model or attempting to find a better estimate for that parameter would be highly recommended, if say just small percentage changes could lead to a disproportionately large change in the model's evaluation. If, however, the model is not unduly sensitive, then it might not be worth the effort in finding a better estimate. Moreover, such a model could be regarded as being reasonably robust, and its reliability to it comparing well to reality is more likely to be dependent on the reasonableness of one or more of the model's assumptions. Despite the usefulness of sensitivity analysis, to keep things simple as well as so to maintain the momentum of this report, we shall forego sensitivity analysis, at least for the time being. This section is concerned with calculating a value for v by substituting the appropriate values into equation 16. Here is a list of statistical values relevant to our model. The origin of each statistic can be found in this video's description. Thus, from our list of statistical estimates, we may assign the following parameter values for equation 16. As for TC and TW, we recall from the overview of methods section from the last video that assumptions 9 and 10 led us to an equivalent of 24 hours for TW. And so because we require all units in SI, Scientific International, we have Therefore, by substituting these values for our parameters into equation 16, we obtain Hence, the model predicts that Father Christmas's sleigh will need to travel at an average speed of just over 2 million meters per second. That is equivalent to about 1,322 miles per second, or 4.8 million miles per hour. Now that's pretty speedy. So, Father Christmas, just how do you do it? Some might say it's all down to magic. Well, it's official. It's all down to the magic of Christmas. Oh, and a bit of math too. Well, that's about it for this video. In the next video in this series, we shall be continuing the modelling cycle and beginning the evaluation process of the model. And so until next time, it's a very happy Christmas from me, and a ho 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 from him.
Ho ho ho!
Oh, and it's a very happy Christmas from Pumpkin. Isn't that right, Pumpkin? Yes. Happy Christmas. Goodbye.